Okay, hello everybody. My name is Zhanat Kappassov. I'm an assistant professor at Robotics Department, Nazarbayev University. Today I will talk about some aspects of tactile sensing in robotics, also in human hand perception. We created some haptic illusion, and this presentation is done for a workshop on robotic manipulation of deformable objects, and most of my work is dedicated for deformable objects, soft tactile sensors. Thanks for inviting Miguel, Juan, Yusuf. Well, before I start my further presentation, I would like to also thank my supervisors who contributed a lot in my research road. Veronique Perdereau, she is my PhD supervisor in France. Yoshihiro Kanishi-san, he is my supervisor who worked in Japan and Taiwan. And Vadim Mishin, who actually worked during Soviet time and in Russia when I was a student in Tomsk. I would like to thank my colleagues Atakan Varo, who is department chair at Nazarbayev University. Juan, he is now working in France and maybe he will work in Spain. And I would like to thank Almash Timir who did his PhD in UK and now is working as an associate professor at the robotics department at the same time, department chair in electrical engineering of Nazarbayev University. And researchers around the whole world, including Guillaume Walk, Youssef Mezouar, Jean-Pierre Gazot, Kaspar Altoifer, Vincent Hayward, and Vincent Padua, and many others. And thank you all. So today I will talk about that, first of all, about human perception, about people in physiology from some past century. Then I will talk about haptic illusion of squeezing soft object, the work that was published in Robotics Autonomous Letters and with double submission in ICRA 2020. Then I will talk about soft object recognition for detecting soft or rigid objects, so binary classification with another sensor. And we can detect also soft objects based on the vibrations. And I will talk about the current work that we work with tactile glove. I will talk about sleep detection. The work just was recently published in MDPI sensors about the shear force with optical tactile sensor. Again, but this was already third paper that we had been working on optical tactile sensors. Then I will talk about edge tactile surveying on a flexible rotor. Well, this work actually has been conducted during my PhD work, and we just recently managed to publish this work. And finally, I would show some results on negative stiffness actuator. Actually, it's some sort of active surface with inherent touch sensing. Human perception had been studied since a long time, and this is still there is some term called the dark sense of muscles. Some aspects of tactile sensing are not well investigated yet. And Ivan Sechenov, who was the supervisor of Pavlov, who is well known for conditioned reflexes and some experiments on dogs. Sechenov, during Russian Empire time, he worked a lot in Europe with French and at that time German Empire researchers. Interestingly, he found a phenomenon called nowadays central inhibition by Sechenov. He found that our human brain, well, those experiments were conducted on frogs, but still there are some cases show that human brain does the same. Actually, some reactions can be slowed down by the brain. How it was investigated. So on the frog is one of the animals that can live without its brain for quite a long time. So a frog without the brain has all reactions in the spinal cortex. So some reflexes just coded within this spinal cortex. Without the brain, the frog reacts to some oxides very fast. A frog with a brain, in fact, the reaction to acids is slower. So once the acid touches the skin of the frog without the brain, that reaction is faster. So one can conclude from that the sense of touch is tightly bound with the actions. The book is written in Russian, but there are some recent works reviewing those investigations, those contributions done by Ivan Sechenov. So during my work, I'm trying just to investigate and contribute at least a little bit to the big knowledge in this field by creating tactile sensors. So in human hand, that especially in the skin, there are different types of receptors, and it is believed that some receptors are sensitive to slow vibrations, like the slowly changing deformations, and some receptors, fast adapting ones, that named as the Partition corpusculus, are sensitive to fast deformations, though deformations that happen quickly, so to the vibrations. This actually can be used in order to trick the human brain. Since the childhood, we got used to that some soft objects filled with granular particles, for example, with the salt, sugar, or coffee grains. The squeezing of such kind of objects induces vibrations, and we learned by many repetitions that our fingertips actually move during such kind of manipulation, I mean the squeezing. So there is an effect of limb displacement when we squeeze a real soft objects filled with granular objects. So as I said before, there are receptors in the skin that are responsible for the fast changes. Here we have squeeze-induced vibrations. By putting a voice-coil actuator, in fact it's just a mechanical speaker, we can create a similar vibrations. If one would detect the contact force applied by human fingertips, and the motor would create the mechanical vibrations, we can have such illusion, right? We extended that work and we created virtual environment, and for so-called pseudo-haptic illusion. Well, when you look at the virtual reality goggles and you squeeze, and you are trying actually to squeeze, but nothing is moved, though that the interface, interface for virtual reality goggles, and if one would visualize that actually something deforms within the virtual reality goggles, we would really feel that our fingertips are moving. It is called pseudo-haptics. So if the amount of deformations seen in the virtual environment is proportional to, for instance, k times of the applied force, we can vary this constant k in order to imitate various soft objects. In order to vibrate the motor, we actually need to modulate it in some tricky way, that we should modulate that voice-coil actuator so that the amount of vibrations would be proportional to the derivative of force, not just to the force itself, but the derivative of force, the force rate. So we performed some experiments with industrial gripper and tried to match those vibrations that occur on the real object and to the spectral power of the vibrations generated by our voice-coil actuator. We varied 18 parameters, and we observed that actually by applying analysis of variance on real human subjects results, we can achieve various different objects with various stiffness properties, just based on the different combinations of the haptic illusion and the pseudo-haptic illusion. This work has been published in RAW, ICRA, with the presentation ICRA. Actually, we can also detect the object is soft or not. just without any vibrations based on our proprioceptive sensors or just a pressure. In the same way, we wanted to actually observe how can we create an autonomous robotic system that can be used to detect the soft and rigid objects. In this connection, we created a planar robot and its controller is using a robot operating system ROS environment. And with the robot consisted of servo motors that can measure the torque applied to its joints, let's say proprioceptive sensors, and joint angles. We could detect the joint angles. We attached the tactile sensing array, the pressure array, 4x1, I guess, array. And based on just, let's say, if-else statements or state machine approach, we could detect the object either is soft or rigid. This work was published in Symposium on System Integration in 2019, Paris. We can also apply machine learning algorithms. In this connection, we built another new tactile sensor based on magnets and Hall effect sensors. The magnets were attached on sliding pins that were connected to a series of elements as just a simple spring. We developed some printed circuit boards with a 4x4 array of Hall effect sensors, single axis. Then we attached this sensor on a robot and effector and developed some sort of affordance of squeezing soft and rigid objects. Actually, a robot pushes towards the object until it reaches the maximum total force or the maximum force of a single sliding pin of our tactile sensing array. Then we applied dynamic time warping and classification algorithms in order to perform binary classifications of between soft objects and rigid objects. Actually, it was quite useful for detecting spoiled fruits from fresh fruits. Well, those examples that the two examples, they just used only pressure sensors and proprioceptive sensors. But soft objects, as we have seen before in haptic illusion, can vibrate if they are filled with granular particles. So in this connection, we built another system consisting of accelerometers and pressure sensors, barometers. We put it on top of industrial gripper, and we created the objects, balloons, rubber sacks, balloons filled with granular particles. And we put inside those granular particles some foreign body that we 3D printed. That foreign body has a different shape and size from those particles. Then we have filled around 17, I guess, balloons with very different granular particles, bean, coffee grains, couscous, salt, sugar, soda. And we squeeze those objects. Some of them, they were with that foreign body, with that, let's say it's phantom, and half of them, they were just purely filled with only the same granular particles. We detected the vibrations and the force that we applied during the squeezing. Using machine learning algorithms, convolutional neural networks, and classification algorithms, we managed to detect those phantoms, those foreign bodies within the granular objects. Well, convolutional neural networks performed better than the other classification algorithms. And now we have some ongoing work on creating tactile glove. And the tactile glove consists of more pressure sensors and with 3, I guess, on the thumb, index finger, and middle finger. There will be in the middle finger also, 3-axis accelerometers. So here you can see the visualization of those sensors on the glove, the pressure sensors. The goal is actually to detect the tumor phantoms in the breast. The application is quite interesting, and we create our own silicon-based prototypes. We 3D print the molds for silicon. We use different rubber with various shortness. We can actually create one layer with rigid, a bit more stiff layer, and inside we can fill with very soft rubber. Another application of tactile sensors is sleep detection. Besides the sleep detection, we can actually also detect whether the object is slipping or sliding. Our target is to detect that the motion type, slipping or sliding, or maybe nothing is moving. For that, we created another setup with accelerometers, with custom-made fingertips, in order to isolate those paddings, the contact area, from the gripper. We inserted silicone fixtures with some nicely tuned softness. Actually, first on our first prototype, we put springs, and then we replaced those springs with silicone fixtures. The 3-axis accelerometers were connected on the fingertips, on the left fingertip and the right fingertip of an industrial gripper. Well, we also created our own data acquisition hardware. We didn't want to use National Instruments data acquisition cards, and we developed an STM microcontroller-based ADC module that can be connected in cascaded way. Well, a computer, when you connect that microcontroller to a computer, that microcontroller is seen as an audio input, microphone, or it can be any type, 8-channel audio input. In order to label the data, we created an instrumentation setup with optical linear encoders, very precise ones. Thus, we could see the velocity of slippage and the velocity of sliding. Actually, there were 2 optical encoders in order to detect the slipping velocity and the sliding velocity. These were the data that we acquired. It consisted of 3-channel accelerations on every fingertip, and the labeling data was given by those optical encoders. We used 3 different objects: wood, plastic, and aluminum, and we placed them in 3 different angles, or 4 different angles: 0, 15, 30, and 45 degrees. The velocity of those sliding and slippage was also varied. Well, and using convolutional neural networks and long-shot time memory, we got 95% accuracy in motion detection. I mean the slippage, sliding, or no motion. Also, since different textures causes different mechanical vibrations, so we managed to classify those 3 objects. Interestingly, the orientation of the sliding and slipping motions could be also detected. Important result that I have found for myself is the bandwidth of a system that is still fairly enough for detecting the slippage and the texture. Our system was sampling the data at 8 kilohertz. So we artificially downsampled the data so that the system bandwidth would be 31 hertz only. And we could see that 25 hertz of the bandwidth, well, it's 500 hertz of sampling rate almost, is fairly enough for detecting the motion type, detecting the slippage using the Vibro-tactile sensors, in our case, accelerometers. It could be also microphone. Well, this work was published in MTPI Sensors this year. Yerkebulan Masalim, our master student, now is pursuing a PhD degree in Sorbonne University with Vincent Hayward and working for Actronica startup. Well, another student who also did a lot of work with me, Daulet Baymukashov, is now a data scientist in an AI center in Kazakhstan. He is also looking for a PhD. With him, we worked on optical tactile sensor. So we created finally, it's our third tactile sensor that we created together, and the second optical tactile sensor. So finally we managed to make a robust design for soft paddings, and we managed to extract the contact location and the forces from images by applying deep learning. Thanks to the fiber optics, we could put that tactile sensor away from processing electronics, so that theoretically, but practically also we showed that it's possible to put our sensor inside the water without any danger to the electronics, even with the pure sealing, because optofibers are not prone to any electromagnetic and short circuit issues. So we created a silicon-based optical tactile sensor. Here we show the process of silicon molding. This sensor has multiple layers. The first layer is made of a quite strong rubber. The rubber with some higher shortness, the rubber that is more rigid actually. And we injected black opaque powder inside the silicon rubber while the curing process. Then the second layer is a colored one. You can actually make any type of colors. In this picture we show red and yellow colors. This layer is very soft and thin. Then there is a transparent layer of even softer silicon mixture. This layer should be really transparent, as underneath, after this layer, we put an array of optofibers that guide those colors, the pattern into the image sensor camera. There are also lightning diodes, lightning fibers. So those fibers guide the white light emitted from light emitting diodes into our fabricated sensor. Then this scattered light and reflected from the colored surface would be seen by our image camera through sensing fibers, let's say. In our prototype, there were around 70 optofibers that would guide the image into a camera, and around 60 optofibers that were emitting, delivering the light from diodes, light emitting diodes, LEDs. Well, when a shear force is applied to such a sensor, that pattern would shift. Some optofibers, they would change the color from one to another, in this case from yellow to red or from red to yellow. This amount of deformations can be detected, and we can actually apply then image processing techniques in order to estimate those shifts. Thanks to this pattern that looks like a disc of a car, we can detect the torsion, the torque applied to the sensing surface. So the middle of the pattern should not change then, and only the surrounding the fibers on the circumference of the sensor would shift a lot. So the color code of those fibers would change. In order to detect the normal force, we actually in purpose made the colored surface very soft, so that the outer layer that is more rigid and more tough would deform this very thin and soft colored layer. And when an object, external environment, applies normal force. At the same time, the sensing surface actually deforms such that there is a protrusion, there is a penetration into this silicon sensor. That colored pattern actually would deform in such a way that the black surface would actually occur in the camera image. This is due to the Poisson ratio. Actually, the Poisson ratio of our outer layer is lower than the Poisson ratio of this colored layer. This is actually, especially this type of normal force sensing in this location is really new in optical tactile sensors. Then we, in order to create a data set to apply deep learning models, we pushed on around 1,800 points randomly selected on this sensing surface. In order to actually detect the shear deformations, there were around 1,000 random directions on X-Y plane. Then torsion deformation, to detect the torque applied to the sensing surface. There were like around, again, 1,000 repetitions, so that end effector would apply torsion around the z-axis, the axis that is normal to the sensing surface. Convolutional neural network was applied in order to classify the contact type. So we would find that either it's a normal, or there is a protrusion in the sensing surface, or shear or torsion. Then regression is applied in order to detect the contact location and the amount of force applied to the sensing surface. The details are in the paper that was published in this year in RAW. Well, interestingly, that the root mean square error in our sensor is high in some of the fibers that are not on the circumference. Normally, in such sensors, the precision is lower as you closer to the border. Maybe it's due to the non-perfect optofibers, or maybe the placement of the optofibers. So all of the 70 optofibers must be aligned very equally on the surface of the sensor. It might be the case that maybe the sensor was a bit shifting, or those optofibers were not immovable. They maybe were moving a little bit during those experiments. Well, still, the accuracy was fairly enough for detecting the contact location and estimation of the forces applied to the sensing surface. In addition, we also tested our sensor for bandwidth. And well, the bandwidth, the mechanical bandwidth of our sensor is limited by its hysteresis. Since this object is soft, it's silicon based, there is a hysteresis, and I guess it was 31. The area between this two curve release and squeeze actions at 4 Hertz, that the RMSE value, root mean square error, was increasing. So at the low frequencies, that error was lower than at high frequencies. That clearly shows that there is a mechanical bandwidth of the sensor itself also. We also were limited by our robot arm performance, that we're not able to move fast enough. And yes, our ongoing work is to integrate also the optical tactile sensors with the Franco-Amical robot arms and perform, for example, reinforcement learning-based manipulation. Well, such an optical tactile sensor can be used for a more, I would say, real-time tasks. as for example, in edge tactile surveying. I have been working on this during my PhD studies, and I developed this tactile surveying controller based on the piezo-resistive tactile sensing array. In edge tactile surveying task, we just need to finely control the contact frame in the Cartesian space. So the contact location and the depths of the contact, let's say, the deformations from the rest state, then the rotations around all three axes are important to control. Even in non-ideal cases, as for example, when there is a partial edge on the sensing surface. So here is an illustration of an edge surveying task over some flexible metal bar with a tactile sensing array. So there are some ways to increase the area of contact with the edge of an object. However, there is an assumption that we more or less know the location of that edge in order to come to the contact with this edge. Otherwise, tactile surveying controller would not work, as there is no contact. Once there is a contact, we can control that contact frame, and while propagating over of some object that is flexible, that object deforms, and thanks to the tactile surveying controller, the robot end effector can adapt finely to that to changing, so let's say quasi-statically changing contact frame. Here is a video from sliding over such a flexible rod using tactile surveying controller. This work finally was published in Robotics and Autonomous Systems this year. Well, here is the real speed, real time, no any acceleration of the video. The end effector adapts to the rotation, the deformations of the flexible object, flexible bar at every time instant. Well, those interactions, the physical interactions at real time, can be sometimes hard and may cause some damages. As for example, no motion to motion, no contact to contact state during this phase of the contact with the environment. The impact force can be high enough. Torque control robot arms can deal with that, but for example, if you still have some position controls robot, those impact forces can be dangerous and may break the object, the system, or the robot arm itself, or the environment. In this connection, there are some structures that can absorb the impact forces and will preserve. Yeah, will actually save the robot from such kind of high impact force. Those structures are negative stiffness honeycombs, and some they are created from beams that can actually buckle. At the buckling moment, the stiffness of the structure is negative, so that the structure actually helps to deform. If there isn't some external force applied to that structure, at some point this structure actually helps to deform to the external force. Using such kind of structure, one can create an actuator. So we took a very simple linear actuator. We connected some servo motors so that we could modulate that negative stiffness structure. We can create a setup with ground truth force sensor. All the signals were connected through one data acquisition board. Then here you can see how such structure actuates, and only this last buckle that shows that there is the buckling here, negative stiffness. You see the force goes up, then decreases. it shows that at this moment there is a buckling effect. Well, here we don't see those buckling effects clearly because of the 3D printed structure using plastic PLA that actually does not have good properties. For this case, a nylon printed structures work better. They actually buckle better. Why? Because of the elasticity. They are not as elastic. Conclusions of these works I can summarize as follows. So human perception can be tricked by vibrations. In the haptic illusion on soft granular objects shown that robotic soft object recognition can be achieved using both vibration sensors and pressure sensors. 250 Hertz of system bandwidth is fairly enough to detect slippage and classify various textures. The optical tactile sensors can actually enable nowadays robots to perform reinforcement learning on a real setup, not on the simulation, but on a real setup, since these optical tactile sensors are really robust. They do not wear off and tear off as the piezoelectric tactile sensors. But the surface is quite robust, so that for thousands or 10,000s of repetitions, the silicon layer can stay at the same condition. There is a lot to investigate with the negative stiffness actuators, but those negative stiffness actuators can be used as active surfaces that can detect and actuate simultaneously. So detect the contact state and actuate at the same time. And thanks to the variable stiffness behavior, one can change the stiffness of the system faster than with an usual robot.